So question 15 from the practice exam, they give us these 6 different molecules and ask us to classify ones that are polar and those that are non-polar as well. They asked us what of these are polar. And so to figure out if a molecule is polar, so number one, all of these bonds are polar bonds because chlorine is more electronegative than sulfur. Fluorine is more electronegative than sulfur, and the same with phosphorus. Fluorine and chlorine are more electronegative than phosphorus. So what we have to consider is the geometry of these. And so in this first case, we're trigonal bipyramidal, and basically both of these chlorines are 180 degrees apart. So they cancel out, their vectors cancel each other out. They're pulling electron density away from the phosphorus, but that tug of war is a tie because of the geometry. And we're going to see the same thing around the equatorial position because all 3 of these fluorines are pulling the same strength from this position. So they're going to cancel out as well because it's that trigonal planar arrangement around the equator. So that would make this molecule non-polar. However, when we go to the next molecule, it still has fluorine and chlorine, but we've changed the arrangements. And so now if you want to look at that vector, right, fluorine is more electronegative than chlorine. So I'll try to draw that vector, to make it look like fluorine is pulling electron density away from phosphorus. It's 180 degrees away from this chlorine. That chlorine is also trying to pull, but it's not as electronegative. So it's not pulling as strongly. So here we would get an imbalance of electron density, and that would make this molecule polar. We would see the same thing here as well because of that. The fluorine equator is also going to be stronger than the chlorine. So there's a lack of symmetry that makes the molecule polar. When we go to this case, the next case, right, we're going to have the same issue where I've got 1 chlorine on that molecule. So it's going to be overpowered, right, by the 2 equatorial fluorines. So that would be polar as well. We go down here, we're going to see the same issue, right? We don't have symmetry. So that fluorine is going to outcompete that chlorine on the equatorial positions, on the axial positions as well. So we're going to have a lack of symmetry. This molecule is polar. In our octahedral arrangement here, we notice all 4 fluorines, right, are 180 degrees apart. So they cancel each other out. The chlorines are 180 degrees apart. They cancel each other out. So that's non-polar. And then the last example, yeah, we see the same mismatch of chlorine versus fluorine, where again, this is more electronegative. So it's going to have a stronger pull of electron density away from that chlorine. So that would make that molecule polar as well. So all of these are polar bonds. The next step is, what is the geometry? Do those vectors cancel each other out, or do they add together in any of those cases?
And just like one last question. So you can tell if like the bond is polar because the central or like the molecule, like I'm just like you said before that like the chlorine is like more electronegative than it's like determined by like whether or not the central atom is more or less electronegative than the surrounding atom.
Yeah, because we want to go, right, we can go back to the periodic table and that trend that we talked about, and we can see that, right, fluorine is the most electronegative element, right? Phosphorus, we're moving down and away, so it's less electronegative. The same with sulfur, we're moving down and away. There we go, that caught up. So it's going to be less electronegative than fluorine. So in all of those cases, the central atom is the least electronegative atom in those drawings. We did look at other things like water, where the central atom is the most electronegative, oxygen in that case. But that's an outlier because typically we make these structures by placing the least electronegative atom in the center. But yeah, once we get to organic compounds, nitrogen and oxygen, there are cases where they are in the center and they tend to be more electronegative than what they're bonding to. But here, yeah, phosphorus and sulfur are less electronegative than fluorine and chlorine. So we're just looking at the geometry of how do those chlorines and fluorines pair up? Are they symmetrical or unsymmetrical in that structure? Yeah. So methane, it is symmetrical, but the reason why methane would not be polar is because the carbon hydrogen bond is not a polar bond. Yes, it is symmetrical. So a better example would be like carbon tetrachloride, where chlorine is more electronegative than carbon, but in that tetrahedral electron domain geometry or molecular geometry, all 4 of those chlorines cancel out and it would end up being non-polar. We can make it polar if we, switched out, if we lose that symmetry and we put in, methylene chloride here, it's got 2 chlorines, 2 hydrogens. Now it's polar because now we've lost that balance, right? We're pulling electron density away and the hydrogens can't balance that out. They are not electronegative compared to carbon. So they're not going to pull electron density away from carbon to help balance that. Yeah, so that's a good question to review, right? It's more than just the symmetry. It also has to have polar bonds. So a carbon hydrogen bond is non-polar. So yes, it's symmetrical, but it's non-polar for other reasons as well.